Hello, everyone. My name is Dirk Colbury, and I'm the lead investigator in the Sea Insight Group, where we do scientific image understanding. So, a little bit of background. Scientific image understanding has been around for a long time. We've always used our eyes for visual observation. The earliest scientists did this. Early biologists often would keep field journals where they would take measurements and draw pictures of what they saw. And heck, they would even hire artists to go with them so that they could get really photorealistic pictures as a way to taxonomize the animals and plants they were seeing. But then photography was invented. And so once we had the ability to put things on film that we were seeing in the world, this was a way to record without analyzing. So you could now record the world as we see it and then analyze it later. Film photography led the way to digital photography, which now is a way to transform how we gather data. I mean, digital photography has made image gathering extremely cheap, almost free. Heck, most of you have multiple cameras in your pocket and are using them day to day for a wide variety of things. And so generating data is easy, but analyzing it is still pretty hard. And so let me give you a quick example. A friend of mine, Fred Dyer, and I worked on a project where we were trying to track the movement and eye position of chameleons. He was really interested of looking at where chameleons were looking in the environment. And we'd run these experiments using 5 cameras. And so each of the cameras would have a different view of the chameleon, all in an arena. And then each camera was running at 30 frames per second. And each experiment took about 5 minutes. And that one experiment would take about 9,000 images. And we'd have many, many, many experiments and trials that we would run using this. So in order to annotate those images, what do we do? Well, we would hire someone. We would basically sit down in front of the computer and frame by frame, click on the screen on where the individual points are for the chameleon's feet and its eyes. And this is very time consuming and takes a lot of time. So we hire graduate students because they're cheap. Or we hire undergraduates because they're even cheaper. And what's really nice about this workflow is that you can run it in parallel. And so we can hire lots of people, but not everybody has that many resources. And what we really want to do is use machine learning, right? The problem is machine learning needs annotated data. You can't learn this stuff in a void. So no matter what, a researcher has to annotate a bunch of data. And the hope is we can use that annotated data to learn a model and then use that model to annotate all future data. The idea is to limit the amount of data that you need to analyze. The problem is you need a lot of data and you need it to analyze, and that's expensive. What happens is that most science, and we call this the long tail science, is exploratory, right? You are experimenting on, you're not exactly sure what you're measuring. You might just be observing the world, or you might be doing a preliminary measurement and you're not sure it's worth the time to try to build a custom piece of software to do your measurements. And if you want to use machine learning, you have to annotate everything anyways. And so when the problem is medical imaging or autonomous vehicles, where there's lots of data and we're doing lots of highly overlapping related machine learning problems, no problem. We can use machine learning there. But when you have a lot smaller sets of data or a lot more exploratory science, it gets harder. And frankly, that's where most science is. And the problem with long-tail science are manyfold. So data annotation is expensive. Every time you ask a new research question, chances are you need a new set of features, which means you need a new program to identify those features. And it's a circular problem. And sometimes the amount of features you need annotated is less than what it would take to do machine learning. And so it's kind of a chicken and egg problem. Sure, you want it to be automated, but you still need to annotate. And so it's an ongoing problem. Our approach is to build tools that helps the research annotate the images. We do that, we call that in the foreground. And so we're trying to build, point selectors and whatnot. But then as they're annotating the images, we're sending what they're annotating to a computer. And we're trying to make the computer figure out what they're doing. We're using machine learning to say, what is it this particular researcher is doing? And can we find an algorithm to help them? Sometimes yes, sometimes no. But worst case, they still have to annotate their images. So one of our very early prototypes, this is many years old now, was called CamView. And what it did was we would pick the points that we were interested, called landmark points, and then the software tried not to make too many assumptions about what was being made and look through different point selection or landmark selection algorithms to try to find the best ones. And if it did, it would start making suggestions. And so we had this automatic system that could find landmarks, and then it tried to find the characteristics of the landmarks that the researcher was looking for, and then use that to start making suggestions to the researcher. So the idea is once they've picked a few landmarks, the system can go forward and make predictions. Often they can't, but sometimes they can. And if we can, we're trying to save researcher time. Another example is image segmentation, which we're currently working on now with C-Segment. The idea here is researchers want to look at the shape of things. And so they often are doing something called segmentation, which is separating the foreground from the background. The foreground is what we're interested in, and the background is what we're not interested in. And some of these problems are frankly quite easy, but it is hard to get a researcher to know all the algorithms that are possible. So consider this simple plant example, right? All they want to do is measure the size of the plant to show how well it's growing and how efficient the plants are. And what algorithms could we pick from to do this segmentation if we were engineers? Well, if you looked at the Python scikit image package, there's a whole library of segmentation algorithms. Here's 13 of them, for example. And they all work on different problems in different variations of success. And so it's the engineer's problem to try to pick one of these algorithms that work best for their problem. And that's actually kind of hard. An experienced engineer even finds it difficult to know which one to pick. And a new person to image segmentation, maybe a biologist, has no way of knowing which one to pick. So it's a very difficult problem to solve. So we're going to use something called genetic algorithms. We use GAs to search the algorithm space. So we define our problem as a vector of all possible algorithms and their parameters. And then we define a fitness function, which says how good our solution is. And then we have the researchers, again, paint the image with what they want to segment. And then the software in the background will go through the different algorithms and try to find a segmentation algorithm that matches what we're painting. And then it will, this is just a prototype view. You can imagine that as you're painting, the algorithm is looking in the background and it say, hey, here's one that we think might work, or here's another one that might work, or whatever. And then you can choose to click on one of those algorithms and use that as your solution and then maybe clean it up, or you can continue painting your existing solution. And the idea being is making a tool that makes not only the annotation part of the problem faster, but also maybe if we're lucky, we find an algorithm that does the annotation for us.